3I Atlas just shifted its orbit against gravity, raising serious concerns among scientists.
Something remarkable has just unfolded in the depths of space. The 3I Atlas, an interstellar visitor hurtling through our solar system, has been examined by the James Webb Space Telescope (JWST), and the observations reveal mysterious lights and unexpected phenomena within its coma and tail. This guest from beyond our system is not behaving like typical comets, and the lights seen may well push our understanding of what constitutes a comet, an interstellar object, or perhaps something entirely stranger. Before we start, smash the like and subscribe buttons for more updates. When JWST trained its powerful infrared gaze on 3Y Atlas on the 6th of August 2025, using its near-infrared spectrograph instrument, the data immediately flagged anomalies in its light signature and outgassing pattern. The comet's coma, the diffuse cloud of gas and dust that envelops its nucleus, glowed in ways not typical of known comets. The spectrum revealed a dominance of carbon dioxide (CO2), far greater than ordinary comet behavior, and water vapor much lower than expected. The term mysterious lights in this context refers to the unexpected signatures in the infrared and near-infrared wavelengths. Bright emissions, scattering effects, and possibly internal heat or luminescence that are not readily explained by standard cometary models. At first glance, one might expect an interstellar comet to behave similarly to the ones formed in our own solar system. Ice sublimating under solar heating, dust and gas trailing off, a tail formed, brightening as it approaches the sun. But 3I Atlas is different in several key respects. Its trajectory is hyperbolic. It came from outside the solar system and is simply passing through. It is the third such confirmed interstellar object after 1I Oumuamua and 2I/Borisov. Because of that, every detail counts. Its composition, brightness, structure, and behavior may carry hints of its origin and the conditions from which it emerged. What makes the lights in 3I Atlas especially intriguing is the possibility that they are not solely the result of simple sunlight illumination or standard sublimation of ices. Some scientists have pointed to the possibility of internal processes, heat sources, reflections from unusual surfaces, or even technological artifacts, though the latter remains extremely speculative. For example, in a Sky and Telescope article, it was noted that the object might be producing its own light. JWST's infrared imaging and spectroscopy suggest it is outgassing CO2 at unprecedented levels, with water significantly suppressed. That means the lights and emissions we're seeing may be tied to chemical and physical processes far less common than those in comets we know. In visibility, the lights manifest as bright spots or glows in the coma and possibly within the nucleus region. The mapping of gas and dust by JWST shows scattered light at 1.2 which highlights dust, emissions at 4.3 CO2, 2.7 H2O, and 4.7 CO across this object. These wavelengths correspond to energetic processes and suggest that 3I Atlas is not simply a dead, icy rock, but an active body with internal complexity. The images hint at structures within the coma that might be brighter or more concentrated than a homogeneous dust cloud would produce. This could suggest localized jets, hotspots, or regions of concentrated reflection or emission. One of the more remarkable findings is the ratio of carbon dioxide to water. JWST found a CO2 to H2O ratio in the coma of 3I Atlas that is among the highest ever recorded for a comet. Comets in our solar system typically release large amounts of water vapor as they approach the sun, because water ice is the dominant volatile. But 3I Atlas bucks that trend. So little water vapor, so much CO2. That implies that either it formed under very different thermal or chemical conditions than our solar system comets, or that it has undergone significant alteration by radiation or other processes in its voyage through interstellar space. The presence of unexpected nickel and cyanide emissions further complicate the picture. Observations by the Hubble Space Telescope and ground-based telescopes have detected nickel vapor and cyanide emissions, substances that are typically found in solar system comets, but not usually in such proportions or with such characteristics. These components might contribute to the mysterious internal or surface processes that generate the lights and emissions observed by JWST. Why should any of this matter? The lights inside 3I Atlas are more than just a curiosity. They open a window into a realm of astrophysical inquiry that intersects composition, origin, interstellar travel, and possibly planetary system formation far beyond our own. If 3I Atlas formed around another star in another protoplanetary disk, then its internal structure, chemistry, and behavior are records of that distant system, one we might never directly visit. The fact that we see these lights or emissions means that the object is active enough or composed in a way that the processes within it are still functioning or responsive to its new environment around our sun. One immediate implication is about formation environments of icy bodies in extrasolar systems. The high CO2 content suggests formation beyond the CO2 ice line in a protoplanetary disk, a region where temperatures were low enough that carbon dioxide could freeze out. That region may have different mechanisms for incorporating volatiles, dust, and radiation exposure than our solar system's equivalent. If the object is indeed rich in CO2 rather than water, this suggests that its birthplace may be colder, or that it evolved differently, perhaps exposed to intense cosmic radiation that removed surface water ice and left behind more refractory volatiles like CO2. Another implication is how interstellar objects are modified by their journeys. 3. I-Atlas has already traversed vast distances through the interstellar medium, exposed to cosmic rays, stellar winds, and collisions with interstellar dust. The lights or enhanced emissions we see might reflect damage, heating, or alteration wrought by those environments. The fact that the water vapor signature is suppressed could mean that water near the surface was depleted by radiation or heated off long ago, leaving behind CO2 ice deeper in the body. The bright lights might then be from regions where heat is coming from inside, perhaps via internal insulation, or from jets escaping that interior region. These are not typical of standard solar system comets. Seeing these lights also raises questions about how comets evolve and how volatile materials survive over billions of years in the cold depths of space. If 3I Atlas is older than our solar system, as some estimates suggest, then the persistence of activity and the presence of volatiles like CO2 indicate that icy bodies can remain active even after long interstellar journeys. That challenges assumptions about how long cometary ices survive unperturbed and how such objects may behave when entering a new star system. Observing such an object so closely with JWST provides a unique laboratory for understanding long-term preservation and transformation of cometary nuclei. On a larger scale, the discovery prompts reflection on how many such interstellar objects might pass through our system undetected, and how many of them might be similarly odd or hold surprises. The lights inside 3I Atlas demonstrate that interstellar visitors might not simply be like solar system comets, but extra. They might carry signatures of totally different formation conditions, evolution histories, and internal processes. That means our classification of comets and small bodies might need to widen. Perhaps the term comet itself may need modification in the interstellar context to include objects whose internal structure or composition defies the norms we know. The significance of this extends to planetary science and exoplanetary system formation as well. If the object did indeed form in a remote star system, its chemistry might represent the building blocks of planets in that system. The CO2-rich composition could hint at how volatile delivery in that system differed, from the way water-rich comets delivered volatiles to the early Earth. The lights and emissions we see are the active signatures of those building blocks in motion, presenting a live narrative of extrasolar materials in transit. That means studying 3I Atlas gives clues about planetary systems across the galaxy, and about how they might differ from our own. Moreover, the patterns of light and emission seen by JWST may inform us about internal structure, how porous or compact the nucleus is, how the dust and ice layers are arranged, how heat flows through the material. If the lights are due to subsurface heating or jetting from interior reservoirs, then 3I Atlas may possess a layered interior or heat-retaining core that has survived long interstellar travel. That suggests that some small bodies are far more robust than our models assume. It also suggests the possibility that internal cavities, thermal gradients, and active surface areas may exist in objects beyond our system. For planetary defense and exploration, the observation underscores the need to treat interstellar objects as wildcards. While 3I Atlas poses no threat to Earth, Its perihelion is about 1.4 AU, and its closest approach to Earth about 1.8 AU. The fact that it exhibits such unusual behavior means that interstellar visitors might arrive with unexpected compositions or activity. If ever a mission were mounted to intercept or study such an object, the lights and anomalous emissions inside would be a primary focus. The window of opportunity is narrow. 3I Atlas is already on its way out, and every day counts. From an astrophysical perspective, the lights reinforce the value of JWST and other high-sensitivity instruments in studying small bodies. Previously, comets were largely studied from within the solar system with ground-based telescopes or with flyby missions. Now, with JWST, Hubble, and other space telescopes, we can peer into the physical and chemical guts of an object from outside our system and see things we've never seen before. Bright interior emissions, unusual high-energy processes on surfaces, and volatile compositions that challenge expectations. The brightness and resolution mean that 3I Atlas is not just a faint speck in the sky, but a target for detailed spectroscopy and imaging. Another implication touches on cosmic chronology. If 3I Atlas is indeed significantly older than our solar system, some estimates suggest billions of years older, then the lights may carry signatures of primordial chemistry from an ancient epoch of the galaxy. That includes volatile compositions formed in early star-forming regions, exposure to galactic cosmic rays over eons, and possibly materials not seen in solar system comets. In that sense, 3I Atlas is a museum piece from deep galactic history, and the lights we see are its preserved signals. Observing them gives us a time capsule into the pre-solar environment. The mysterious lights invite speculation, responsibly and scientifically, about alternative origins or mechanisms. While the consensus remains that 3I Atlas is a natural object, a comet or comet-like interstellar body, the mere fact that some of the lights or emissions do not match the standard model means that scientists are exploring whether internal heat, layered ice structures, high radiation exposure, or even unknown physical processes might be playing a role. In particular, some researchers have raised the possibility of technosignatures, telltale signs of extraterrestrial technology, though the evidence remains suggestive at best. While the lights are far more likely to be natural, the very exploration of such possibilities expands our mindset about what could wander into our solar system. In sum, the detection of mysterious lights inside 3I Atlas by JWST is a landmark event. It puts a spotlight on an interstellar visitor behaving in ways we didn't expect. It challenges our understanding of comets, small bodies, and interstellar objects. It hints at exotic chemistry, unusual internal structure, and faraway formation histories. It underscores the power of modern telescopes in revealing minute, barely visible emissions in objects light years away. And it invites an expanded view of what our cosmic neighborhood might hold, how many interstellar wanderers might pass through, and how much they may teach us about the galaxy beyond. The luminous signatures detected within 3I Atlas shine as silent heralds of its exotic provenance. The radiant glows and peculiar emission patterns picked up by James Webb Space Telescope speak volumes about the internal workings of this visitor, casting light on its history, its journey, and the environment it originated from. These lights, though indirect, elusive, are essential clues. They trace processes of release, reflection, sublimation, heat dynamics, and possibly even structural relics of a faraway birth, unlocking an unprecedented window into interstellar immigrants that pass between the stars. Those lights become comprehensible when one understands that 3I Atlas is not merely a frozen rock that drifts inert through space. It is dynamically responding to solar radiation, responding to its passage through the inner realm of our solar system, and emanating signals of composition, structure, and evolution. The brightness and spatial distribution of those luminous regions, whether in the form of concentrated jets, a delineated bright coma region, or hotspot emissions, suggests that beneath the apparently uniform halo lies a more complex interior. The concentration of glows in certain directions hints at anisotropy, patches of enhanced outgassing, localized dust jets, or thin surface crusts breaking open to expose interior volatile reserves. The interplay of the mysterious lights with dust, ice, and gas illuminates again, metaphorically, the layered structure of the object. In particular, the infrared spectral maps captured by JWST reveal that the light emissions correspond strongly with the presence of carbon dioxide CO2 at around 4.3 water vapor at approximately 2, 7 carbon monoxide CO at approximately 4, 7 and dust scattering at 1.2 The significantly strong CO2 signature means that the glowing regions inside the coma are dominated by that molecule, making the brightness effectively a tracer of volatile outflow. That dominant CO2 signal is itself mysterious. It may reflect an origin near the CO2 ice line in its parent protoplanetary disk, or prolonged exposure to cosmic rays which transformed other volatiles into CO2. The light thus becomes a kind of chemical fingerprint, glowing not only because of illumination but because of chemistry being acted upon by solar heating. The spatial pattern of luminosity further suggests directional preference. The gas and dust appear to stream more strongly on the sun-facing side, with the bright spots concentrated in the region where solar heating is most acute. That suggests that the mysterious lights are not uniformly distributed but are tied to the thermal gradient across the object's surface and possible internal conduits of gas and dust. The comet's activity appears to be asymmetric, with a plume of material that may look brighter on one side, jetting outward in ways that generate internal reflection, scattering, and emission. In that respect, the lights are an echo of the internal plumbing of the object. Channels, fractures, subsurface pockets of ice, insulated by dust and crust, now bursting open or leaking under the increasing solar warmth. Beyond the mere detection of those glows, the brightness levels themselves provide constraints. The fact that 3I Atlas is already showing strong activity while still more than 3 AU from the Sun at 3.32 AU inbound during JWST's observation means it must harbor volatiles capable of sublimating at relatively large distances, volatiles that warm and break away more easily than water ice at those heliocentric distances. That again ties the lighting to composition. CO2 and/or CO sublimation are the likely drivers rather than water ice, which typically starts to dominate nearer the Sun. In that sense, the mysterious lights are signposts of deep freeze volatiles still intact in the visitor's interior. The implications of these luminous features stretch into the realm of formation and evolution. If the code of 3I Atlas is rich in CO2 and poor in water compared to solar system comets, then the lights we see serve as a window to its birth zone. Volatiles freeze out at certain distances in protoplanetary disks, so a CO2-rich surface suggests the object formed beyond the CO2 ice line, or underwent transformational processing such that water was stripped away or suppressed. That in turn means the mysterious lights trace back to a different chemical environment, and likely a different radiation environment, than that of our early solar system. The brightness thus codifies the history. Moreover, the intact nature of the volatile reservoirs implies that 3Y Atlas has not been severely stripped by interstellar travel despite its journey. The lights are evidence that active processes remain. If cosmic rays or stellar encounters had entirely eroded its volatile banks, one would expect far lower emissions. Yet the bright glows show that the visitor still retains the means to produce pronounced outgassing. The survival of these volatiles underscores that interstellar bodies may preserve much longer and remain active well after leaving their birth systems. The lights reflect endurance as much as they reflect origin. Then there is the structural dimension. The lights help diagnose the nucleus's physical state. For example, if the internal structure were monolithic and unfractured, one might expect more uniform outgassing and a relatively smooth coma brightness. But instead, the observed brightness variations and concentrated emissions suggest patchiness, fractures, faults, or structural weaknesses where the heat penetrates more deeply, allowing volatile release. That means the mysterious lights may mark places where the crust is thin, where dust mantle is broken, where sublimation is channeled. They effectively light up the architecture of the nucleus's outer layers, turning invisible structures into observable signatures. The effect of dust must also be considered. The lights do not all come from gas alone. They include scattering by dust and thermal emission of dust grains heated by solar light or by interaction with outflow. In some images, the dust halo appears brighter than expected, and that brightness can be attributed to freshly released dust that reflects sunlight or glows in the infrared as it warms. The interplay of dust scattering and gas emission means the mysterious lights speak to both composition gas and texture dust, tying the physical processes together. The dust may carry with it ices, organics, and metals, and the glows may trace fine grains being lifted off the body, spreading the chemical signature outward and enabling remote observation. A further implication lies in the evolutionary story of interstellar objects. If the lights of 3I Atlas tell us that its outer layers have undergone prolonged cosmic ray processing, as one recent paper proposes, then those luminous patterns are the final echoes of that processing. The paper suggests that cosmic rays can transform CO into CO2 and build organic-rich crusts over tens of meters of depth. That means the glows, specifically the CO2-driven jets, are revealing not primordial pristine interior, but a processed shell. In that sense, the mysterious lights show not just where the volatiles are, but where the work of galactic radiation has already been done, and how deeply into the object we are seeing. The lights therefore trace both fresh activity and cumulative history. From a broader astronomical perspective, the ability to pick up these lights with JWST represents a watershed. Until now, interstellar wanderers have been fleeting, faint, and difficult to study in detail. The fact that an object from beyond the solar system is shining so clearly, showing distinct glows in the infrared, means we now have a new class of targets where internal or surface structure become observable. The mysterious lights confirm that interstellar comets can be more than passive glints. They can be active bodies with measurable behavior. The implication is that each such visitor may carry a bright message, literal glow, that scientists can read. This opens a new era in interstellar small body science. When a visitor from another star system enters our domain and begins to warm, it may light up in ways that let us read its record. The faint glows, the jets, the dust, the scattered light, all become chapters in a story of origin and travel. The mysterious lights of 3I Atlas thus herald more than one observation. They hint at a methodology for future interstellar object studies. Observers will look not just for motion and orbit, but for internal glows, emission lines, dust scattering, and structural diagnostics as standard practice. In terms of solar system science and planetary system formation, the lights also serve as comparative markers. By contrasting the glows of 3Y Atlas with comets native to our solar system, we can highlight differences in formation environments. For solar system comets, water ice sublimation frequently dominates once inside approximately 3 AU. Their glows are dominated by H2O-driven activity, and their dust comae behave accordingly. But 3I Atlas is different. Its glows favor CO2, and its dust release and gas jets may follow alternative pathways. That comparative contrast enhances our ability to distinguish between solar system and extrasolar bodies. It may even cause a rethinking of how we classify comets. Maybe interstellar comets deserve their own category, defined by glowing signatures and composition, rather than only orbit. There is also a cautionary tale in those mysterious lights. They remind us that surprises await. The glows of 3I Atlas were stronger and more chemically distinct than many expected. Scientists anticipated some difference, but not this much deviation. That means we must remain open to phenomena not yet predicted. The discipline of small-body astrophysics must be ready for visitors whose lights do not match our templates. Observing these glows demands flexible instrumentation and fast responses. The light is fleeting as the object quickly recedes. The lights thus are both opportunity and challenge. One cannot ignore that these luminous signatures might also bear on future missions. Suppose humanity were to send a spacecraft to intercept a similar interstellar visitor. The bright glows would provide crucial targeting and diagnostic information. Where the jets are, where the dust fields are densest, where the volatile outflow is active. The lights map the dynamic regions of the nucleus. For mission planners, these glows could be beacons, guiding where to aim sensors or landers. The fact that 3I Atlas lights up in infrared means that mission instrumentation should include sensitive IR spectrometers and imagers tuned to these wavelengths. The lights, thus, practically inform design. At the symbolic level, the mysterious lights inside the object underscore how little we know about the deep galaxy. We tend to imagine our solar system's comets as archetypes. But 3I Atlas shows that outside our system, the rules may differ. The lights reveal alien chemistry, alien formation, alien journey. They hint that each interstellar traveler carries intangible information, encoded in light, emission, dust, that we are only just learning to decode. The lights inside it are messages from another star system, speaking in wavelengths, waiting for us to listen. Furthermore, those lights raise existential questions about preservation of volatile-rich bodies in the galaxy. The fact that 3I Atlas retains sufficient volatiles to produce bright jets implies that the interstellar medium and long durations of travel did not obliterate its activity. That suggests that many more such active wanderers may populate interstellar space, still holding internal stores of ices ready to glow when they near a star. The mysterious lights invite the possibility of a hidden population of active interstellar small bodies, each carrying a potential lab for galactic chemistry. The glows also challenge the notion of dead interstellar rocks. Without these lights, one might assume an interstellar object is inert, cold, and dull, a chunk drifting silently. But here, the lights show that when lighting conditions and proximity to a star change, these objects may awaken, shine, and reveal themselves. That means there's a dynamic aspect to interstellar small bodies. They may lie dormant until warmed, then produce sudden bursts of brightness, jets, and dust. The mere presence of light means processes are underway. In that regard, monitoring the temporal evolution of the lights becomes essential. As 3I Atlas moves inward toward perihelion, the lights are expected to change, grow in intensity, shift pattern, maybe new jets form, dust release intensifies, and the composition of the outflow might evolve. Tracking those dynamic changes will help us correlate light patterns with heliocentric distance, sun object angle, thermal gradients, and internal structure. In essence, the lights are not static. They are an evolving symphony of activity, and by watching their tempo and pitch, we learn the architecture of the object. The brighter the lights become, or the more complex they appear, the deeper we can probe. A further subtle implication is that the lights may allow us to gauge age and exposure history. For instance, cosmic ray processing would create a refractory crust whose properties differ from fresher ice layers. If the luminous emissions are carried by jets breaking through that crust, then the lights mark where that crust has been breached, giving a clue to how long the object has been exposed. The brightness distribution is thus indirectly a record of age and of interstellar journey. That means the lights inside 3I Atlas help tie together chronology and physical condition. There's also a connection between the lights and the object's surface albedo and reflectivity. Bright patches might reflect sunlight sharply because of clean, icy exposures. Others might glow because of thermal emission of warmed dust. By mapping light intensity and distribution, scientists can infer surface parameters. Which areas are dark and insulating, which are fresh and bright, where heat penetrates. The lights thus serve as diagnostic of surface texture and material. That adds another dimension to the data. The lights are not only telling about release, but also about surface properties and how heat flows. On a more speculative front, the nature of the lights invites imaginative possibilities. While no serious evidence currently supports alien technology, the fact that the glows do not match entirely expected patterns means that scientists remain open, if cautiously so, to non-standard mechanisms. Some of the luminous features might be due to subsurface heating from radioisotopes, or perhaps the result of structural collapse exposing fresh ice pockets. The unknowns remain large. The lights are the first whispers of these unknowns. They demand interpretation, but also humility. In the context of planetary formation and volatile delivery, the lights of 3I Atlas remind us of the vast diversity of chemical environments in the galaxy. If an object can form with such a high CO2 reservoir and then produce light signatures accordingly, that means that planetary systems elsewhere might incorporate volatiles in different proportions. The glows we see from this visitor may thus echo the volatile budget differences in ancient disks. For example, if CO2 dominates rather than H2O in some systems, then the delivery of water to planets and the potential for life might follow a very different trajectory. The lights inside this object hint at that possibility. From an observational strategy standpoint, the detection of these mysterious lights highlights the importance of rapid multi-wavelength follow-up when interstellar objects are discovered. Prior to 3I Atlas, the second interstellar object 2I/Borisov was studied, but without the suite of sensitive IR instrumentation that JWST provides. The fact that the lights were so clearly visible means that future survey systems, detection networks, and space telescopes must be configured to capture these luminous manifestations quickly. The lights therefore influence not only science, but also policy and instrumentation. The faint gleam radiating from deep within 3I Atlas now stands as a testament to cosmic endurance and transformation. Every flicker of that light represents an echo from an ancient world, perhaps one that orbited a sun long vanished or drifted in a region of frozen silence between the stars. As the James Webb Telescope continues to trace its spectral whisper, astronomers find that even the smallest variations in brightness encode vast histories. Chemical reactions sculpted by time, atomic rearrangements seeded by radiation, and thermal pulses ignited as it awakens in our star's warmth. The lights shimmer not as steady beacons, but as living, shifting threads of motion, breathing evidence that something dynamic stirs in this interstellar wanderer. They challenge the limits of our comprehension, forcing us to redefine what activity means in the emptiness between suns. More than a scientific anomaly, the glowing heart of 3Y Atlas is a mirror held up to cosmic evolution itself, showing that energy, change, and memory persist even across unimaginable distances. Each photon reaching Webb's mirror carries a story billions of years old, bridging two star systems and reminding humanity that the universe, though vast and silent, is never truly dark. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on the mysterious lights James Webb detected inside 3I Atlas? We want to hear from you. Thank you for watching and see you next time.